Hello, this is Dr. Jack Jackson with Part 8 of our series of lectures on descriptive statistics. Today we're going to talk about changes in data. So the questions we're interested in is on a distribution, how does it change? Does it change over time? If we take the measurement at a different time, what happens in that situation? We might be interested in a particular statistic like how does the counts of something change over time, how does the actual output data change over time, but we can also be interested in things, does the entire distribution change over time? But also, does it change if we change something in the input? For example, if we look at two subclasses of the data, is there a difference between those two classes? If we're looking at the manufacturing, if we have two assembly lines making the same product, is there a difference in how the two lines are performing, for example? We might look at a broken line graph. In a broken line graph, we have data points that are graphed, just like x and y coordinates, and we put dots there, but then we connect the dots with line segments. So we only use this kind of graph when we have continuous data, at least on the input variable, so that it makes sense. Points on those lines should actually be actual data values that occurred somewhere in there, or at least approximations of those points. Perhaps some points that we didn't know of what happened in between the two things. So for example, where they might be heights, as the height is changing over time, we measured at two places. Well, we know in between those two places that the height existed. Okay, so there's some sort of continuous connected curve that connects those 2 points. It may not be a straight line, but it's some kind of curve. So the easiest way to connect them up would be just with a straight line segment. If the input variable is called a time, the graph is called a time series graph sometimes, and it shows changes over time. So broken line graphs are really good about showing change over time. So when you have a graph, particularly a broken line graph, you might ask some things about, are there patterns in the data? In fact, that's probably a good question to ask anytime we're looking at a data set. So in particular, when we're looking at time series graphs or broken line graphs over time, do we have any kind of long-term trend? Is it on average going up or going down? Is it an increasing or decreasing function? Do we have any short-term trends? What's happening, right now? Do we have any unusual values? It's going along about the same, and all of a sudden we have an outlier pop up. Do we see any cycles? A lot of times things go in cycles. You'll see it go up and down and up and down. There might be other patterns. So do you have any kind of patterns? And if you do find a pattern, you're going to want to ask yourself, well, what caused these patterns or changes in the data? What did it all of a sudden, it was going along at a certain level and all of a sudden now change to a higher level? Well, something must have occurred there to make that change happen. If you can identify that, that might help you in controlling the process, or maybe for the future, or making predictions. So just an example of a time series plot or broken line graph, we'll go back to our data that we've been using for these examples of the age of inauguration of U.S. presidents, and these are the ages of all the presidents in the order that they served office. So this is again the age at their first inauguration. So it's not exactly time on the horizontal axis because some of the presidents served for different lengths of time. So for example, Washington, the first one was 8 years, but then the second one, Adams, was only 4 years. Some only served just a few months, and of course somewhere in here we have President Franklin Delano Roosevelt, who served for a long time, much longer than any of the other presidents. So it's not exactly time here, but almost the same thing. It's the order that we have them in, and we have their age. So we might look at this and see, do we see any pattern? I don't really see any real noticeable pattern here, but if we had seen, for example, that they started high and they ended low, that would indicate that over time we've shifted towards younger and younger presidents. That didn't really happen here. We see jumps up and down. We don't always see a young president after an old one, or an old one after a young one necessarily. So there's not any real discernible pattern to this particular data, but in other data sets you might have that. It does point out some things, though, that, for example, right now, President Obama, this one on the last dot, is one of the younger presidents we've had. He's one of the 5 or 6 youngest ones of all times, whereas we just had a couple of the real older ones here not too long ago with President Reagan and George Herbert Walker Bush. Another thing we might want to do with data is compare two different groups together. These might be two completely different samples, or we take a large sample, we might want to look at two subgroups or two subsamples for that. And we want to say, well, what's the same and what's different about this? And then, are the differences significant? Are they the result of natural random variation? Now, when we get to that point, we're really getting into what we call inferential statistics that we're going to get into a lot later in the course. How do we quantify that? That's really where inferential statistics comes into play. And of course, then ultimately we want to know, well, what caused the differences in these samples, or what is the significant factor that's different that made these things different? When we start getting to that, now we're starting to really draw some conclusions from the data, and that's eventually what we want to be able to do. So, for example, we might say by party. Is there a difference in the ages of the party? Now, in this particular one, we've done the party of all the presidents. Some of these are not really useful. For example, Unionists, there was only one person who was a Unionist party, and you will see that of course, that's the minimum, the maximum, the median, the mode. It's just one data value. So that's really not really helpful. And really, the Democratic, Republican, and Federalist, and even the Whig Party, those don't have enough presidents to really be that useful. But there's lots of Republican presidents and lots of Democratic presidents. And so we might compare just the Democratic and the Republican here, and we can see some interesting things. Is there anything that we might notice about comparing these? Well, we could see, looks like on average the Republicans are a little older. Not only do they have this one outlier, the oldest one, the median's a little bit higher, and this, the first quartile in particular is quite a bit higher. But they do go down and actually have the youngest one as well. So there's a little bit more overall spread, but the middle half is a little tighter than the Democrats. The Democrats are going to be a little bit more evenly spread out through here, but overall not as spread out as the Republicans. I'm not sure if there's a lot of significance there, but anyway, you can look at some data sets and compare. So you can look at box plots side by side and see if there's any kind of comparison that you might make, and maybe you can make some conclusions, and maybe you really can't. Here's some data that's kind of interesting. This is from the beginning, 1928, I believe it is, to 2003. My data stops at that point, of the ages of the actor and actress who won the Oscar for Best Actor and Best Actress. And here's a dot plot of the data. I think you can look at this data just looking at the dot plot and can kind of already reach some conclusions. Even though the oldest one was a female, and by far the youngest was a female, if you look at the bulk of the data on the females, is basically quite a bit smaller, younger age than the males. So this is an interesting thing, because it looks like the males, they're allowing higher ages to get those good roles and do well in those roles and be recognized, whereas those roles that they're awarding for females are quite a bit younger. Same thing here when a grouped histogram, and you can see the same information here but in a grouped histogram form. Same kind of conclusions as well. And we can look at a box plot. That's another way of comparing these side by side, and you notice here that you can definitely see that this middle half of the females is definitely lower than the middle half of the males, and really even the females that are older, really all these points up here are kind of considered outliers, where only this one actor is considered an outlier. So in general, but overall, counting outliers and everything, the female best actresses are more spread out, more variable than the best male actors. So it looks like there's definitely a bias in the Academy there of awarding older males versus younger females. And notice we have some way down in the lower 20s for the youngest. In fact, several females, a quarter of them, over a quarter of them, in their 20s, whereas there are hardly any males at all getting an award in the 20s. And 3/4 of the actresses are below 40 there. Probably that's actually 39. 39 and below, 3/4 of the actresses. Whereas to get 3/4, you're going to have to go up to about 48, looks like, on the males.